Today we're going to get on to lecture number 11, which is about two-way slab design. And this a two-way slab is different to a one-way slab because you can generate moments in both directions as long as your breadth does not exceed less than half of your length. And I mentioned that when we did the one-way slabs last week, but I'll show you what the slab looks like. There is a typical plan view of a two-way slab, and these are the peripheral beams. And so what we want to do is work out what the moments are on the slab, including the negative moments over the beams in both directions and the positive moments in the middle, because if you assume that this was elastic, which it is to a degree, it sags like this as it goes from beam to beam and sags between those two beams. So deflection, or the sagging amount, is quite an important criteria, but we will cover that today. Now, as the name implies, two-way slabs transmit bending action in two directions between the supports. These slabs are usually supported by rigid beams or walls around their periphery. These slabs can be designed using sophisticated computer analysis, utilizing finite element analysis, or the simplified method as in AS3600, and that's what we're going to be doing today. So there is a line drawing. This dotted area there, or the area enclosed by the dotted line, is where your main moments are. The moments near the supports peter out, and they're not very big at all. So you usually just use nominal steel there, apart from the steel that runs over the supports, which is negative steel, and that is often bigger than the actual positive steel in the center of the slab. The slab is divided into a middle strip equal to 3/4 of the effective span and two edge strips as shown above. So that there is 3/4 of the overall distance between the supports, centers of the supports, and in the LX direction as well. Most of the bending action is carried by the middle strip, and that's what I said to you previously. The small bending action in the edge strips is catered for by the minimum steel ratio. So we put minimum steel in around the edges, but I'm not talking over the support. Note that when the ratio of the long span to the short span exceeds 2, then the slab becomes a one-way spanning slab. So if that was 6 meters and this was 3 meters, it would be a two-way slab right at the limit. But if this was 12 meters and this was 3 meters, or even if this was 7 meters and this was 3 meters, it would be a one-way slab, and you would just design it as we did previously. Now, table 732 is a table of bending moment coefficients, beta x and beta y, used so to find the respective bending moments. Now, this is the table, and I'll just run through it with you. The short span coefficients beta x, and remember this is the short direction of the slab. The values of Ly over Lx are these coefficients here, right up to a maximum of 2, and that's what I just referred to earlier. That there is 1. That slab there is square, actually, and that goes up to the maximum rectangular size that you can design in this manner of 2. Now the edge conditions, 4 edges continuous, 1 short edge discontinuous, 1 long edge discontinuous, and if you take the first one, we've got this situation, and there's another slab adjacent to it there, and there. So those edges are all continuous. 4 edges continuous. If you made this edge discontinuous, in other words, this was the edge of the building, like this, then you would have three edges discontinuous, but it would be one long edge discontinuous. This would be category 3. This would be one long edge discontinuous, and so forth. And that's how you actually select the coefficients that you're going to use. Now, getting back to this, note that while the short span coefficient beta x, beta x varies with the span ratio of Ly over Lx, beta y remains constant. This beta y remains constant. Okay, it's the long span coefficients for all values of Ly over Lx. The negative bending moment at a continuous support is 1.33 times the maximum positive moment in the same direction, and you will see that as I work through the problems we're going to be looking at today. The negative bending moment at a discontinuous support is a half of the maximum positive moment in the same direction. So we will be looking at all those situations today. These are symbols used in these calculations. You can go through them at your leisure, but you will see the application of them today as we go through this. I have actually duplicated those symbols where necessary. Now we're going to do an example. For the suspended edge slab shown below, determine the following. All appropriate positive and negative moments. We've got to do a guesstimate or an estimate of the slab depth first. The flexural reinforcement layout, and then rationalize the layout for bar diameters and spacing, and that will become obvious to you as we work through these problems today. When we rationalize it, you don't use the purely theoretical answers that you gain from doing the calculations. You have to be practical. And then third thing, whether the deflections are satisfactory using the deemed to comply method. So here we have a two-way slab with a long edge discontinuous. The three other edges are continuous, and that will help you select the right coefficients from the table. The dimensions to the center lines of the beams. The beams, of course, are 300 wide. The mass of the concrete is 24.5 kilonewtons per cubic meter. Cylinder crushing strength of the concrete, 32 MPa. And the ultimate tensile strength of the steel is 500 MPa. The solution. There we just draw up a line diagram to jog our memories. That's a discontinuous long edge, a continuous long edge, and two short continuous edges. So it is 14 meters by 7 meters. We estimate the slab depth, let's say a thumb suck, 7 meters. We always work on the short span, 7 meters divided by 40 to give us a ratio. And that gives us, say, 170 millimeters. So the mass of the slab then, the mass per square meter is 0.17, because it's 0.17 meters thick times a square meter, which is 1 times 24.5 kilonewtons per cubic meter, 4.17 kPa. The ultimate load of the slab, including the live load, is 1.2 for G multiplied by the mass of the slab plus 1.5 times the live load. 9.5, say 10 kilopascals, 10 kilonewtons per square meter. An estimate of the negative moment in the short direction is, Ly over Lx, as I said to you before. You need that to enter the table. It's a factor of 2. And your biggest moment is going to be the negative moment on the this continuous edge over here, over there. Let me just check on that. Sorry, on the continuous edge, 1.33 is the factor. So we have 1.33 times bx times the ultimate load multiplied by the span squared. And we have a presumed moment of 43 kilonewton meters. Assuming cover of 30 millimeters, maybe 20 millimeters cover plus 10 millimeters the center of the steel, gives us an effective depth of 140 millimeters. We can now check our M over BD squared using your graph, and you'll find that using that moment, we're using unit width of slab. Don't forget that. We use a 1 meter width of slab when doing slab design, multiplied by the effective depth squared gives us 2.2. We've taken 3.5 as a lambda figure because it gives you a reasonable sort of solution. You're not overstressing the slab. And what I've said here is this is okay. So the depth of slab is 170 millimeter. It's okay for flexure or okay for bending, but deflection might control depth. Probably not shear. I don't think we're going to have a shear problem. You won't have a shear problem on the slab. We now do the moment fields. Now, let me just find that table again. Here we are. Our moment field there is 0.066. Where did I get that from? We have a one long edge discontinuous slab. It has a Ly-Lx ratio of 2. So your short span bending coefficient in that particular case for item number 3 is 0.066. 0.066, that's what that coefficient is. The long span coefficient for all beta y for all values of Ly over Lx for the 0.066 case is 0.028. And there we have it, 0.028. Okay? On our discontinuous edge, we multiply that factor, the 0.066, by 0.5 as mentioned earlier. On the continuous edge, we multiply that factor by 1.33 to get a new factor. For this one here, we multiply it by 1.33 as well, because they are continuous edges, to give us factors of 0.037. From this, we can now compute our bending moments. And how do we do that? The bending moment is beta times the ultimate load times the span squared. And we then get an answer in terms of beta being the moment. So we've got 490 beta. So going through this now, and I think you can see the whole thing, we start multiplying the 0.033 by 490. Gives us 16.2 kilonewton meters. And that's a negative moment over this beam, on the top of this beam. And 16.2 kilonewton meters. Over here, we do the arithmetic, we get 43 kilonewton meters. Over here, we take the long span moment and we multiply it by 1.33, and we get a negative moment over there of 18.2. It's the same on this end. And in this way, you garner all your bending moments. So you do the moment fields from your table. You then calculate your bending moments in terms of beta, and you end up with this table there showing you your actual bending moments. This 32.3 kilonewton meters is the bending moment between there and there, the positive bending moment. The 43 here is the hogging or negative bending moment over the beam. The 16.2 is the hogging or negative bending moment over the edge beam, which is there's nothing beyond that. And in the same vein, we have negative bending moments over the two end continuous supports. We now check our steel depth in the LY and LX directions. It's always worth drawing up a little, making a little drawing like this. And remember that you want your short span steel tied below your long span steel. Why? Because as you've seen on the previous page, we generate the biggest moments in the short span direction. And to do that, we want the biggest effective depth we can get to make the steel work in the most efficient way. The moments in the long span are not as high, so we can have less effective depth. And that's the reason we do that sort of thing. And yeah, our actual calculations are for exposure A1, a 20 millimeter cover. We're assuming N16 bars both ways. We've got an overall depth of 170 minus the cover minus 8 millimeters. This is for the important steel, the bottom steel. So we've got an effective depth for D1 of 142 mil. D2, we've got 170 for our slab minus the 20 cover minus the 16 millimeter diameter bar minus the radius of the top bar, which gives us a lower effective depth of 126 millimeters. If you don't understand that at the first hit, play the video to yourself again and you'll understand it, or you can always contact me. We now determine the steel content. So I've drawn up a table there. We look at the short span first, primary moments. You see we've got 16.2 there. That's that negative moment there over the discontinuous edge, that one. The 32.3 is your maximum positive moment in the center of the span. The 43 is a negative moment over the continuous edge of the long span there. And then we've got on the long span, which is a steel running this way, we've got a maximum positive moment of 13.7, and where we've got the slab going over the supports, negative moment of 18.2. dx is your effective depth, which we've just worked out up there, 142 and 126. So for our short span, we've taken the higher effective depth, and I'll explain the reason for that earlier. For the long span, smaller effective depth because the moments are smaller, as you can see. I've got phi equals m over bd squared. We usually use the Greek symbol lambda, but anyway, leave it at phi. We take the m over bd squared, and if you do the arithmetic, that is this bending moment converted to Newton millimeters divided by the breadth in millimeters, which is 1,000. We're working on a 1,000 millimeter wide strip. And d squared is this effective depth squared. And you do that for each of these moments, which will give you each of these lambdas or phis, as we've called them, for the short span and the long span. Our steel ratios that we get from that, because the steel ratio, as you remember, is the area of steel is PBD, so we have to work out what P is. We look at the graph and we find out what P is. In this case, for that m over bd squared, or that lambda, it's 0.0022. For this moment there, the P is 0.0044 of your graph. For this one, 0.0058, and the long span 0.0026, and this moment 0.0028. So the area of steel then when you work out PBD, is per meter width is 312 square millimeters. Second case on the short span, and 824. That's that big internal negative moment on the long edge. And looking through your tables, you can then select steel. That's the area of steel in square millimeters per meter width. Look at your tables, and I'll just grab them here just to refresh your memories for those who've forgotten, and I trust nobody's forgotten if you've been conscientiously going through your lecture and tutorial notes and videos. You select your bars, the design area, you select, spacing of bars, bar diameters, and you can find out what spacings you can put them at. So that's what you do there, and that's what I've done here. From that I've used N12s at 300, N16s at 320, N16s at 240 for that steel area, N12s at 300. So even though we said we were going to use N16s everywhere, we've actually just jumped and used N12s. You're not going to affect the design at all. In fact, you're going to make it's going to be stronger, because if it's a smaller diameter bar, you're going to have a bigger effective depth. So I wouldn't worry too much about that. And then, so there your basic steel areas are for the moments and the steel ratios we worked out. Now, I've got a note at the bottom here. The area of steel is the area in millimeters squared per meter width of slab, and I've said that many times. The minimum area of steel is 0.2% per meter width. That's the minimum steel. 0.2% of the gross area of the slab, in our case 170 by 1000. So it's 0.2% of 170,000, as I've worked out there, and that's 340 square millimeters per meter width. And for that you would have to use N12s at 300, because your bar spacing according to AS 3600 94111 is the lesser of twice the thickness of the slab, or 300. Your slab is 170 thick, so if you use 2D it would be 340, but it's the lesser of that, or 300, so use the 300 for your minimum steel areas. Right. We now do a basic reinforcement layout based on the figures that we got from that last table where we did the calculations for steel areas. This line there is the outside, or call it the center line of the slab. Okay, 14 meters by 7 meters. We're taking 0.75 of that, because that's that area. As I said to you, the positive moments outside of that, that width plus that width are very small, negligible, and the same in the long direction. So these are the bars then that we selected. N16s at 320s for your main positive steel. N12s at 300 negative steel there. N16s at 240 for this bigger negative moment there. And N12s at 300 both ends, because both those ends moments are exactly the same. And yeah, we've got, I've mentioned that, and I call that typical because there we could use N12s at 400, but that's incorrect. We have to use N12s at 300, as you'll see. You could theoretically use that, but you'd be going against the code's recommendations. We now rationalize the reinforcement layout. And this is what happens every day. You don't work it out exactly theoretically and then do it like that. You try and do it in a way that's workmanlike, that the steel fixers and the carpenters and the foremen and the project manager and everybody can handle. You don't want to get into esoteric, silly dimensions. So you make things reasonable. And that's what we've done here. That's why we rationalized this reinforcement layout. And what we've said is, we're not going to use N16s at 320 there. We'll just make N16s at 300. It's a bit more steel. N12s at 300 for the smaller moment in the long dimension. All the way along there, N12s at 300. Because the assumption there was incorrect anyway. You can't put them at 400. It has to be 300 in this particular case. N12 negative steel over that beam, on top of that beam at 300, ditto over there, negative steel along this beam, N16 at 200. And then use deemed to comply standard details for bar lengths and extensions into spans. As I said to you before, in the one-way slabs, you can carry half of the steel through onto the support and you can curtail the other half. Or what people do is they stagger the bars. They'll run this one bar through to there, the next one 300 away, they'll run to there and they'll cut it off there so that near the supports you're only getting 50% of that steel running through onto the beams. Right, so we're going to look at the deemed to comply deflection criteria, and I mentioned that at the beginning of this lecture where I said you can use finite element analysis, computer software to work out deflections and so forth, but it's a good idea to learn how to do it by hand, and you can later get onto the simpler ways of doing it by using a computer. So we're going to check the deemed to comply deflection criteria. If you can satisfy this equation, then you know that the depth that you've chosen will be satisfactory, taking into account the loads you have. This is the effective length, LEF, and this is the effective depth of the slab. K3 and K4 are factors. It's a factor for a slab. K4 is another factor. Delta over LEF is your 1 over 250 as a deflection coefficient. This is Young's modulus or elastic modulus for the concrete, and we'll come to that. And again, this is the total load on the structure, on the slab, FDEF, per meter width. And the code gives you this formula there, FDF, which is 1 plus KCS little g plus psi s plus KCS psi l, all multiplied by Q. Now, KCS again is a factor where you take into account compression steel if you have any. This formula there. We haven't got compression steel, so we're going to be left with 2 for KCS, as you can see there. G is the dead load that we worked out per square meter in the initial calculation, which was 4.2 kilonewtons per square meter, plus psi S given to you in the loading code is 0.7. for short-term creep and deflection, plus 2, which is the KCS, times 0.4, 0.4, which is psi L, the long-term creep and deflection coefficients, and Q is the live load, but not factored. These loads aren't factored, as you'll see. So we just check out what KCS, CS, if we had compression steel or steel in the top fibers, or we had 2 layers of steel, we would have to work out a different KCS. But once you've done this, you find that it's only 2, only the 2 remains. These are given to you. You can look them up over there in 1170.2, that's the loading code. Substituting those into the formula, we get 1 plus 2, which is KCS, all multiplied by 4.2, which was your original dead load of the slab, plus the factor given to you psi s plus twice plus 2 times 0.4, also the factor given to you for the long-term creep and deflection, and that whole bracket multiplied by the applied live load unfactored. Gives you a figure of 17.1 kPa. If you look in the code, you'll see that K3 is 0.95 and K4 is 2. I'll cover that a bit more thoroughly in the tutorial to follow this. You can use this formula here to work out your elastic modulus for the concrete, but I've found that this one is fairly satisfactory. It gives you an answer very similar and very close to this particular answer, and it's a lot quicker. Just 5,000 times the root of the concrete cylinder crushing strength. I think it works at about 28,400 and something. But we'll use this one, which is a result of this typewritten computation there. Now, our allowable deflection that we're going to allow for in 242 and AS 3600 is span over 250 or 1 over 250. So to calculate LEF over D, we put in our knowns into this equation which appeared at the top there. Put them into the equation, and we get a figure of 35.8 when you've done this arithmetic. Okay? Now, LEF is the lesser of 7 meters or 6.7 meters if you started really cut it fine. If you wanted to, play it safe, you could leave it at 7 meters, which is the center-to-center span. This is the distance between the sides of the beams, 6.87, and we've done that in this particular case, 6.87. So the actual LEF over D is 6.87 over the effective depth of the slab over little d, gives us a figure of 49. As LEF over D equals 49, and we have a limit of 35.8, okay, we've got a deflection problem. And the only way to fix this deflection problem is to increase the thickness of the slab. You could do that incrementally. It's a process of iteration where you actually do the calculation and recheck it. Or you can say, well, 170 millimeters, I'll have a go at doing it at 300 mil. So there you have it. And that concludes the lecture. Thank you.